Okay. Hello, everyone. I am Muliang Shou, and my colleagues in the morning, he talked about how to leverage the QEMU to run native libraries, so Songtao. And now I'm going to talk about a many-to-one virtualization system built on the top of the QEMU and the KVM hypervisor. It's a Type 2 hypervisor. We call it GiantVM. So why do we need many-to-one virtualization? When we scale a resource, we know there's two common ways to do it, scaling up or vertical scaling, or you do horizontally scaling. Scaling up is straightforward. You just put a bigger, more powerful server, and there's no need to, if you have a monolithic type of architecture, you don't have to modify it. You just put in the bigger server. So it's easy, but scaling up usually have a top limit. There's only so much powerful hardware you can fit in a rack. The other way is to scale out. So you basically have you basically do the horizontal scaling. You can aggregate resources with more nodes, use affordable hardware, and but on the opposite side, the networking becomes more complex. You have to also maintain data complex. You have to also maintain complex data consistency. Also, if you have the existing hardware, there might be significant engineering efforts to modify, and sometimes you have to do it invasively. So what we are looking for many-to-one virtualization is to merge the forte of scaling out and scaling up. So we're trying to aggregate multiple physical nodes into a single large VM while using affordable hardware and maintain a single system image. So the developers on top, they don't have to modify and introduce a lot of monolithic architectural refactoring. However, as we all know, there's no super bullet, and in this case, we find that performance is a key aspect that our many-to-one virtualization solution should look forward to. So going back in time, we firstly proposed GiantVM back in 2018 or on KVM forum, which is in Scotland, Edinburgh, I think. So at that time, we have a we have a distributed system that includes CPU, shared memory, and of course I/O. And it was implemented by QEMU 2.8 and Linux 4.8, which is forever before. So the basic architecture is like this. We have multiple vCPUs, and in the distributed shared memory, one CPU writes and it syncs to other CPU via memory CC consistency protocols like Ivy protocol, which we will touch on later. And on the bottom, on the foundational side, we have internet connections, which utilizes RDMA or TCP. Through this distributed memory system, distributed shared memory system, the DSM, we put together this whole synchronization architecture as a Type 2 hypervisor that's going on top of the KVM and QEMU. So eventually we can use it to directly run on Linux. It's like each node runs on the local vCPU, and we focus on interactions that go between different nodes. Like for example, there's IPI, the interprocessor interrupts, memory mapped I/O, and port I/O, and so on. So what we do is we interrupt them by sending forwarding instructions. So we have, like for I/O, we have a dummy I/O APEC, and we just interrupt these requests and forward the instructions to the proper remote node. So we talked about the Ivy protocol, which is mainly a CC consistency protocol. It has 3 states: modified, shared, and invalid. And each page of the memory space has one of the 3 states. So when you read a shared page, and when you write, you become the sole owner of the page, and you invalidate other pages. And during a page fault, if you find yourself having a invalid page, you know it's time to ask the remote and fetch a new page. So The general workflow is that when the guest OS access memory by the GPA, which then you translate through KVM by the EPT, which is the red line here. You go deep into the KVM. So if the memory is not local, a request will be sent to the manager and then forward to the remote memory owner, or sometimes it's yourself. And after retrieving the correct memory, you first write it into the local memory. You mark it as shared to maintain cache coherence, which you can see here as the green line on the bottom left. And finally, the node access the memory content, which going from DSM to KVM to back to the application, which is this blue line here. We find that the performance side is something that we should take care of. And we find that the software-based distributed shared memory system has something we call a ping pong phenomenon, which means the applications may access the same GPA on different remote memory on different remote nodes, which will leads to a DSM page fault because it ping pongs, and the different remote nodes may have the same GPA, and they don't actually know the GPA is shared by everyone. They have the states of their local GPAs, so they just keep requesting the correct pages again and again. And this ping pong phenomenon can be shown when we're doing OS boot. So we can see here there's lots of highly regular lines of conflicts that we can show here. So on the top, we have lines about paravirtualization, which is most notably EOIs, or end of interrupt signals. So you can see those signals are clustered into a few of the memory addresses. On the lower side, it's mainly about the design of the OS itself, because it has shared data, like kernel data or BSS files, and of course, including Jiffies, which is about global time synchronization, and is highly we frequently triggered when you're doing OS boot. We can also see the red lines are clustered around those few memory addresses. Recently, we tried to use Compute Express Link to replace RDMA and TCP and see if we can improve the performance of our system. So a quick introduction of Computer Express Link. It has 3 classes of devices, type 1, type 2, and type 3, which mainly corresponds to the underlying CXL protocols. So the CXL protocols include CXL.io, CXL.cache, and CXL.memory. And of course, when we include this new type of networking architecture, networking hardware for our GiantVM, we use it as a fast network, just like inspired by the work of Hydra RPC, which was introduced in ATC 24. And we put it in place of RDMA and find that we can reduce the data sync time from to cut it almost in half. The next, we improve upon this foundation, and we try to use it for cold hot tiering storage. And we put the hot guest pages that was mentioned back in the OS boot. We put it as in the CXL. So in the data picture here, we can find that by using it as a fast network, we improve the performance of our system almost in half. So, so the average page fault time is in microseconds, cut in half. And of course, the number of page faults goes down by almost 50%. Oh, sorry. To be precise, we use the CXL hardware in the DevDAX mode. The CXL hardware has 2 modes: DevDAX mode and System RAM mode. But the System RAM mode, Linux takes over the management of this memory, so we use it as a DAX device. To implement this. To implement GiantVM with CXL, we have to port it basically from QEMU 2, where CXL didn't happen. So we ported into a more modern QEMU and Linux configuration to QEMU 9 and Linux 6. This work is sponsored and in collaboration with China Telecom Cloud Computing. So a big thank you, shout out for them. So for QEMU, we modify around 3,000 lines of code, and the major of changes are in the newly added interrupt forwarding module. For KVM, we mostly, the new modules are added in by the kconfig, so we can mostly add the new added file deltas. The merging only involves about 400 lines, so it's quite good. And in QEMU, we have basically modified those modules or added in those modules. We have an interrupt router which implements IPI, IO APIC forwarding across different QEMU instances. We have RDMA written here, and of course, for CXL hardware, this is CXL.C and CXL.H. This is basically about page transfer and memory registration through RDMA. We also have distributed QEMU client interface parsing. Also, we have CPU states tags that goes in between different modes. And also, we have local APIC emulation, which is about having a dummy IO APIC and other interrupt mechanisms in the local phase. So in KVM, in Arch x86 KVM folder, we added new files, dsm.c and h, dsm utils. Those manage things about distributed shared memory. To support the Ivy protocol, we create new data structures called kthread, server thread and client thread that enforces the Ivy protocol. It's about 1,500 lines. In the MMU section, we added more about distributed memory, about things like about SPTE table, and how to handle page faults before the SPTE table is set or before the end of interrupts. So for Ivy, we implement our version of Ivy in around 1,000 lines. And data transmission, we have three options. We use the TCP for a proof of concept, RDMA for a more stable solution, and the CXL is what we are looking for right now. So basically using a CXL as a fast network is explored very vigorously in recent academic works. The core idea is that we have a request and response ring buffer for two nodes, and you use memcopy to put the request into the buffer, and then the request goes through IB transactions to enforce CC consistency. The response is a 4K page in our instance, and we fetch the page to get what we want from the remote. So handling a request, as mentioned before, is you use dynamic polling to do this until a response comes out in the ring buffer, and the PCIe, we can actually have PCIe MSI protocol, which can save us a lot of polling here, but it requires a CXL 3.0 and requires 3.0 architecture and its hardware capability to do this, which we are looking forward to have. So after using the CXL as just a replacement, a faster network, we go further to using the memory semantics of the CXL itself. So to do hot code memory page steering. So we modify the EPT entries, and we modify the table to put the hot pages such as the JPs or and point them to the CXL shared memory. So the whole memory hierarchy of our system has actually changed. So before we are fully software-based shared memory, but now we have a small area of CXL shared memory where we can put hot pages inside. To access CXL, it's around 300 nanoseconds, which is around 2 times the NUMA hop, which we think is quite okay when you're considering the whole networking that's involved. And of course, we have the normal software-based shared memory. So if there's no DSM ping pong and everything goes well, it's around 1,000 nanoseconds. If there is DSM ping pong, it's around 10 microseconds. And once we detect that there's a once we detect there's a ping pong, we swap the hot memory into the CXL. So the swap happens when there is a write page fault. So the current local node will fetch the newest data, set all other copy sets invalid, and set itself as the owner of this page. And at the same time, it's mems copy to the CXL shared memory, and you modify the EPT entry. When other nodes access the page, before CXL, you go through the Ivy protocol and you fetch from remote. But now you trigger the page faults, you require the owner, and the owner does not send the 4K page across the internet, but instead it sends a pointer directly to the CXL shared memory. And this is what we got. The light blue is RDMA solution with no CXL involved. Red is when we have the normal CXL, which we use it as a fast network. And the dark blue is when we further implement the swapping, the hot code tiering solution. So we can see the tiering solution has quite a big improvement, almost half to 2/4, two-thirds of the performance, the cost time. So here's a demo about our OS boot, which should complete in 10 seconds. And we can also run some benchmarks on it, like CPU stress, stress NG, in a 48-core VM. The stressing will run for quite a bit, so I'll fast forward. Yeah, and so you can see the, you can see the stress NG benchmark numbers coming out here. So in the future, we are looking forward to run Redis, looking forward to run MySQLs and other benchmarks here. So that's all. This is our project link. Thank you. Yeah, that's correct. They are, thank you. Oh, we haven't actually looked into that, but I think that's a very promising direction. We will look into our future work. Yeah. Yeah, I think that totally makes sense. We can use the upper level information to put into the shared memory, and we can further push the performance. Yeah. Thank you. I think the most we've used is 128 virtual CPUs. For nodes, we have tried, I think, 4 to 8 nodes. If you go above 4 to 8 nodes, the performance starts to degrade a bit. Yeah, so we find 4 to 8, and 64 CPUs is the sweet spot. Yes. Yes, yes. I think it's a, yeah. Also depends on the CXL hardware itself, because I think currently we use CXL 1.1 or 1.0, which is which is intra rack level. So you connect between the racks. In 2.0, 3.0, you can connect it between racks. So you extend it more, and more complex NUMA topology it can support. We do simple profiling on OS boot scenario and the CPU stress scenario, and we find the performance go down a little bit. But we haven't done a more detailed solution like drawing the red horizontal points, which I believe we want to look into in the future. Yeah. Hi. Oh, thank you. It's an honor. We would very much like to upstream this. And we have already open sourced our code in the link, which I think it's this is the old version, the core version, the Linux 6 version with CXL. We want to open source it and upstream that as soon as possible. Uh, so resiliency is something that we hope to look for, but we haven't gone that far. We're mostly improving the performance of the whole system. Yeah. In the next step, we will try to look for resiliency. Sorry, can you repeat the question? Hi.
You mentioned Jiffies, but I'm wondering if there's other things that you run
into. I believe it's most Jiffies, but there are other things that I couldn't remember right now. We can discuss it after this. I can send you that. Thank you.